A classic physics problem is for a projectile motion is the monkey and hunter problem. It is also called motion in 2 and 3 dimensions. So the problem is there is a monkey on a tree and he refuses to come down. He's hungry. So a zookeeper comes up with a brilliant idea of shooting the monkey from a cannon, and he has to get it to the monkey. So how does he do that? Where does he aim so that the monkey will grab the banana and he will be able to eat? So in the first scenario, let us consider there is no acceleration due to gravity. There's no force of gravity. And when the monkey lets go of the limb, he doesn't fall. The projectile, which is a banana shot forward, just gets to the monkey straight away. So now what happens to this banana if the Earth's gravitational field is turned on? What path will the banana take and the monkey take? So in this case, the monkey falls to the ground and the banana goes over his head. Now, the other scenario is that the banana is shot very, very fast. So in that case, the monkey and the banana get together while the monkey is falling. If, on the other hand, the banana is shot very, very slow, the banana will still reach the monkey, but he will have to have traveled a long distance away. So a few things that we need to know about falling objects. Well, falling objects, a projectile's constant horizontal speed is always constant unless there is a drag force, and regardless of the weight of an object, all objects will fall to the ground at the same speed. Another important thing to keep in mind while we go through these derivations is projectile launched horizontally. So if a projectile is dropped or launched horizontally, as you can see, they will both reach the ground at the same spot. See how in terms of their vertical distance, they travel the same amount of vertical distance. And the reason for that is because if they are dropped or launched vertically, the rate is going to be the same because the only force that's acting on them is gravitational pull, and the gravity does not care what the horizontal velocity is. So now that we have a little bit of a background, we are going to talk about what we need to do in basic physics in order to evaluate a motion in 2 and 3 dimensions. So basic classical physics says knowing your initial x, v, and t, you should be able to predict all motions regardless of what time you take. So you should have an x as a function of t, you should have a v as a function of t, and you should also be able to predict for any future time knowing the other conditions. So classically in physics we need equations, right? But which ones and how do we derive them? That is our problem. So let's go ahead and do that knowing the basic fundamental ideas of projectile motions. So this is kind of a long derivation, so I'm going to be using a lot of this space, so I'm going to write a little smaller, and so pay attention while we go through this. So for any projectile motion, as with all physics problems, we are going to start with some initial conditions. So let's say this is my projectile, and I am going to launch it at a certain angle with the horizontal, and I'm going to call it theta, and it's going to have a certain initial velocity v naught. Now, since we are talking about a projectile motion in 2 dimensions, I need to have a v naught x and a v naught y, depending on my coordinate system. So let me assume this is my x and this is my y. Just take normal coordinates, and we are going to have to find v0x and v0y. So if I was to take this projectile, make a triangle out of it, this is going to be v0 cosine theta. This is going to be v0 sine theta, knowing that this is v0 y and this is v0 x. Right? Just a small trig identity will give me this initial condition. The other thing that I know is that my velocity vector is going to be v0 x squared plus v0 y squared. That is going to be my velocity, which is going to be my initial velocity, or my final velocity, whichever velocity, but this is what it's going to be. And since velocity is a vector, I am going to have an angle. So tangent of theta will be equals to Vy over Vx, or theta will be equals to tangent inverse of Vy over Vx. So these are the equations I'm going to need. For now, I'm going to drop these subscript just so that it makes it easier. So you would know that these are all the equations that I'm going to start with. So in order to do these projectile problems, what we need are some initial conditions. And what I've discovered, the easiest way to figure out what this is what I'm going to show you here. So any projectile motion, we know that the vertical component of the projectile motion, as it is going through different parts, is going to be exactly the same. So if I was to draw V0x, it is going to be exactly the same length, right, as it goes forward. And this is going to be my initial theta, and this is going to be my top. Okay, this kind of looks like my top of my projectile motion. And then it's going to have certain velocity in the y direction. So now let's talk about the velocity in the y direction. I know that the velocity vector changes as it goes up. So the velocity, is it going to get smaller or bigger? Until it reaches V, F, Y is going to be 0 at the top, right? And then the velocity vectors keep increasing, 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 increasing as we come down. V0x, on the other hand, does not change. So now how do I put all of this information so that it's on my fingertips? And so this is a table that is going to be very, very useful for you when you solve these problems. So I'm going to make this table, and I'm going to say my x-axis and my y-axis. Now, what are all the things that I can say about my x-axis components and my y-axis components? Well, I'm going to start with my basic information that I know, which is right here. So my initial conditions are going to be my velocity conditions. So velocity is going to be V0x and V0y for initial, and it is going to be V0x no matter where I am, or Vy depending on my distance. So any final velocities, these will not change, but this will. Next step, acceleration. Since the velocity is constant, my acceleration is going to be 0 in the x direction, and it is going to be g in the y direction, and it's going to depend on whether it's going up or down. Same thing with force. If I was thinking about force, the force will be 0 or mg, depending on what we mean by force. It is also going to be its weight, okay, which is going to be mg. Now, knowing all of this stuff that I have in front of me, I can figure out what the possible velocity vectors and the possible acceleration vectors and the possible positions are going to be. So let's talk about position. So for my position, which is x as a function of t, or y as a function of t, so x as a function of t will just be equals to v naught xt. Since v naught is constant, it doesn't change, it's not going to give me anything different. However, this y velocity is going to be depending on this x, which means it is going to give me vy as an equation of motion that I can write as, dx delta y as v0y t minus a half gt squared, depending on whether it's going up or down, right? So acceleration always points downward, so I generally put in a minus sign here so that I'm not confused later on. Anything else that I need to know? Oh, yes. So this v0y should have an equation associated with it. So I generally will put here v0y minus gt squared. Oh, minus gt. Oops. I was going to write a square here. That would be bad. Anything else that I would possibly need? Okay, well, that's a good start. So now we have to find the basic problem. Now that we know all of these are going to be our projectile motion. What is our basic problem in physics? Well, we need to find how high this projectile is and how far it will go. So we were very, very clever, and we called it range, which is going to be how far your projectile went, or h, which is the height of how high your projectile is. So we are going to do certain assumptions. We're going to solve a few problems, and then we're going to find the range and the height for our projectile motion. So let's start with that.